So we have a decentralized physical infrastructure AI that's like on the whole environment or in a collection of environments, learning and improving. And all of that data is actually written to the chain and protected at post-quantum level. So even if your systems are not at post-quantum level, the truth about them is.
Imagine a mesh network of AI-powered nodes that could validate the security of your organization's systems and applications. It's a clever use of blockchain to add security to real-world devices. And best of all, it will feature post-quantum cryptography. Learn how this technology could simplify security and if it may even prevent killer robots in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guests today are bringing the Naoris Protocol to the world. We have David Carvalho, the founder, who was an ethical hacker for 20 years. I put in some decades doing that as well. And we have David Holtzman, Chief Strategy Officer, who created a little something called DNS, you might have heard of, and worked at the NSA and IBM. So welcome, guys.
Thank you. Glad to be here.
Yep.
Yeah, great. And you guys both know a lot about information security, and you're working at the intersection of AI, blockchain, and post-quantum security. So we'll kind of touch on all that. This is the post-quantum world, so we will have to say a few things about the PQC aspects. We'll get to all that. But first, David C., let's start with what the Naoris Protocol is at a high level.
Sure. So Naoris Protocol has the objective of basically taking away the single point of failure principle that every device, every application, every service, every process is in reality right now in the world. So every device, every application, every system, every server is a single point of failure from a risk perspective, from a hacking perspective, from a tampering perspective, to everything it is connected to, everywhere in the world for everything, right? And so decentralization comes in, and that was kind of like an obvious marriage for us. So bringing in, technologies like, DLT, blockchain, cybersecurity together, some of the most mature areas in cybersecurity, AI, and in this case, post-quantum technologies just made a lot of sense to mitigate future threats and current threats. So our objective is to use blockchain technology to fix that problem, which is really nobody's fault. That's just how the internet's made. But to create kind of like a primitive, let's say, a baseline that ensures in a highly cryptographical, resilient environment, trust and assurance across devices, across networks, backed by a decentralized group of validators under what we call a decentralized proof of security consensus mechanism. So in other words, it's kind of like creating a hive mind of systems checking each other, kind of like acting like watchdogs, making sure that they're all in a trusted state using very advanced mathematical algorithms that are very hard to break and therefore bring a lot of resilience to the space. So the more it grows, the harder it is to break. While right now, the more it grows, the more points of failure you have. So that's kind of like our main initiative. And since then, we have branched into, post-quantum capabilities or quantum safe, quantum resistant capabilities, decentralized physical infrastructure, and other areas.
Okay, so for people listening who just get the basic idea of blockchain down, in reality, you have like a distributed ledger and this ability to check what transactions have occurred, and that's how blockchain transactions occur. In this case, you have all these devices that now are a distributed like mesh of devices that are aware of each other, and if something bad is going on, the other ones could be like, well, we don't trust you anymore, right? Is that kind of it in a really high-level nutshell?
That's right. Even between networks that you don't control. Let's say. So let's say you want to access an API that you don't control. How do you know that the system that contains the API or the API itself is not tampered with? If it is, you probably don't want its data. So what you said is right, except the blockchains pretty much operate under a principle that very much focuses on smart contracts and crypto. And so basically the environment that it operates on is about 0.5% of the world economy. So the cryptographic space or the crypto space, DeFi and so on, in blockchains. In this case, it's about bringing blockchain to the real world. It's about bringing blockchain to enhance the baseline, let's say, create security and assurance and resilience by default in existing centralized spaces, thereby decentralizing their capability to trust each other.
Okay. Yeah. Before we dig into a little bit of that, David H., you, I guess, have traditionally been involved in very traditional security, right? Web 2, I guess you could call it, over the years.
Web 1.
Yeah, Web 1, right? Yeah, Web 1 into Web 2, for sure, Web 1. So what made you feel compelled to move into this new kind of approach?
As soon as I heard about it, I was really excited because I guess philosophically, I'm a kind of an anarchist at heart. And I've always been very, very concerned about any centralized authentication mechanisms. I mean, I've been doing this for 35 years, and it seems that the internet started off more or less decentralized. And as commercial entities got in, they kept trying to centralize it, usually under the guise of authentication and then cryptographic authentication. The problem with that is it leads to monopolistic behavior. I was in a company that was a monopoly, Network Solutions, where I worked at. We had the contract for the entire domain name system. And up until 97, 98, you couldn't even sell a domain name unless you went through us. And now it's ICANN. So it's the same idea. I'm also worried about governments. And I like the idea of having a system where the way David's designed it with the resolvers, they could be in a different network. You don't really know what network they are. It's very, very hard to corrupt any potential resolver. And I guess the last point is that I'm really excited about. David said this. I just want to stress this. With conventional Web 2 kind of authentication, the more nodes you add, the weaker the network gets, the more vulnerable it gets. In this kind of setup, it's the exact reverse, because now you have more resolvers and the network becomes more robust. And if you look at data breaches today, I went back and looked the other day, almost every major data breach has that we name at a company like Equifax or AT&T. It really wasn't them. It was a third party they hired for point of sale or credit cards or something. And it weakens the entire system. So that's why I'm excited by it.
Sounds good. Yeah. And before we dig into some of the ways that this works, because it's a little hard to visualize. For me, it's easy to visualize, but some people don't really think about this stuff. I was involved in smart contracts kind of early. I gave the first talk at DEF CON on how to hack that back at DC 25. So, I'm interested in all that. But to take it to a quantum place for a sec, there were claims of quantum resistance that first caught my eye, and why I wanted to have you guys on the show. So maybe you could both take a stab at explaining how this is quantum resistant and what ways that PQC aspect comes in to this.
I can maybe take a swab at that. So basically, we went and we started operating with a number of former NATO leaders that operate obviously in the hardest to defend environments there are, and probably the highest, most important targets under their supervision, let's say. So one of the interesting mandates that they suggested for us was to actually bring a consensus mechanism up, which we call DPOSEC, Decentralized Proof of Security, that uses post-quantum capabilities, post-quantum cryptography principles to actually operate. So that means, both the hashing, the keys, everything is actually following, the best practice defined by NIST, right? Under the one of the winners of the competition for the post-quantum algorithms that actually just finished recently. That was a multi-year competition. And in this case, we worked together with various universities, so both in the US and also in Europe, to do research around those and actually, make it work. So we were we wrote a paper that was chosen by the IEEE Foundation, probably the biggest engineering group in the world. And we went to Cape Town in South Africa to present it. It went quite well. It was well received. And that was in October last year, but we are already working on that for about 3 years. And as the time passed, and we talked to the generals that are our advisors and so on, across various countries in Europe, they just kept saying, every year that this is a bigger and bigger problem, and we don't know how to deal with it. And obviously, if you look at the investment amounts that come into this, and I'm sure we'll speak about this later, everybody that has critical data to protect or mission critical environments is very focused on that as one of the kind of shiny objects incoming. We can see it coming. So post-quantum cryptography for us was obvious, kind of as a next step to do. So right now we are in full production with a post-quantum chain that is the first one operating at that level with about 7,000 transactions per second. And it includes all the capabilities that we said before. Distributed computing, distributed processing under our protocol. And that it does that, so it kind of levels up blockchain to the next cryptographic level, but it also levels up centralized machines to the next trust level. So the way this works actually is that the protocol, it supports this distributed computing and distributed storage. So even if you have it doesn't matter if you have one of these or a server or a Raspberry Pi or a $1 IoT device, it will probably be able to run a node, which is quite interesting because you can enforce things that you can never enforce in IoT. And as you know, and they don't have any enforcement of anything. So that is exciting for us and our partners.
So it's lightweight, but and this leveled up quantum resistant version, which is smaller in building, would that also be able to run on cell phones and things like that?
Absolutely. Both at hardware level for key distribution and PKI, all the way to in hardware security modules, so on, all the way to software level, very likely. And if it is on a network that is discoverable, it will use computing power from other devices to, for example, derive keys and things like this, which is quite exciting. Because if it was only in one device, it probably wouldn't be able to do anything with it.
It is very lightweight, and it's highly portable, which I think is really critical now because of all the different IoT devices, none of which get any upgrades or maintenance, as far as I can tell.
With the quantum resistant version, is the goal to then ultimately replace, to make all of the protocol devices be running that version going forward? Sort of as a parallel of what we're facing right now in InfoSec in general, right? Everyone wants to do this migration now to be compatible with the new NIST ciphers.
To tell the truth, I think we have been helped by NIST. About 2 weeks ago, yeah. they have come out and said, we have chosen the winner, and the winner is one of the ones that we use from the competition. And as they believe, we believe, the intelligence spaces we're connected to and militaries we're connected to believe that as soon as you have a quantum computer with enough qubits or quantum singularity, or call it whatever you want, in the short term, everything that's secret is going to be broken by that actor, and that includes blockchains, that includes RSA, AES, insert acronym here, any elliptic curve-based cryptography, which is really everything. Then they said that it is going to be mandatory from now for any federal agency or entity, for example, in the US, to follow post-quantum principles across their infrastructure and their stack. So there is a big effort on that side. And we know from other contacts that we have, that's going to be mandated under regulation as well for privacy reasons, because, for example, with quantum capabilities, a foreign actor or a state actor, as David was talking about, would be able to do pretty aggressive attacks on anything and just really destroy privacy across the board for whole countries or the whole world at the same time.
Let me add something onto that too, because one of the things that we've heard, we talked to a lot of governments and government agencies, and one of the things they're afraid of, it's probably not all that obvious, but it's store and break kind of stuff. So when they're dealing with government or military, it's just as bad if they get broken 2 years from now or 3 years from now. So the sooner they switch to this kind of, quantum proof cryptography, the better they are, because there's a lot of hell to pay in the future at some point.
Yeah, the harvest now, decrypt later threat.
Yeah,
that's right. Which is kind of funny because it almost doesn't. It almost makes, how can I say, the whole quantum stuff, not matter, and at the same time matter. Like, it doesn't matter if quantum computer is here now or in 2 years or 3. What matters is that the harvest now and decrypt later is going to happen, and in 2 years your stuff's going to be decrypted, and nobody changes keys, right? So whatever you have there in 2 years, you're just going to have more, right?
Yeah. What's the shelf life of your secret, and how important is? Which of the finalists from NIST actually is in the quantum resistant protocol you're using?
It's the dilithium based one. Yeah.
Okay. And you built the new version of the solution around that. You're saying that that's post-quantum, kind of like some experimental post-quantum blockchains exist. Do you then think that this approach could be easily migrated out to the world? Because right now, obviously, one of the biggest problems with blockchain is so many of them are not post-quantum safe. And how are we going to make that switch? Do you have any thoughts about any way that the rest of the industry can learn from this and kind of start a migration in that sense?
Yeah, that's really interesting. So we're talking to really big players in the blockchain industry, like I'm talking like top 10 about that problem, because they see that. And, we have a number of potential solutions to that pass through, for example, post-quantum rollups to, quantum backups of chains and other things that I cannot speak about right now, but they are quite exciting, and I think they're just logical. Nobody that has assets wants them at risk, right? And that goes for the whole crypto world, the ETFs, the whole $116 trillion banking system we have, so on and so forth. So it doesn't really matter if you're in Web 2 or Web 3. The point is that it just makes sense to move into validation structures that, first of all, exist. In most cases, they don't exist. And if they exist centrally, which means they're easily manipulatable. So you cannot trust them for really everything. And I'm talking about say, for example, SMTP, the Simple Mail Transfer Protocol. I send you an email. It's plain text. Like me and David were joking about that the other day. And that's been around for eons, right? Really, technology eons. And it needs a bridge with Web3, in my opinion, right? There's lots of things that need a bridge for post-quantum, a bridge for decentralization, call it whatever you like a transparent connection, right? They don't need to be destroyed because they're important, but there needs to be a plug into something better that allows them to continue to live. Otherwise, it just gets worse. And like I said, people are aware, critical entities, highly regulated spaces are aware. The quantum difficulty, and I'm sure David will want to talk about this, is no longer kind of like an innovation problem or is theoretical problem. It's an engineering problem. So you just need to throw at it enough engineers and enough money, just like with, putting a man in the moon sort of thing, and it will be solved. And there's constant innovations about that. And let me tell you, adversaries, be they who they are, they will want you to think that nothing's happening. That's their advantage while they're actually running. So
that's the APT model.
Absolutely, but at nation state level.
Yeah. It's to get in and just like exist and persist. So what we're protecting here right now, before the post-quantum is fully rolled out, is this this validation, or this like proof of, I guess, what's the word I'm looking for? Like proof of security, proof of integrity, right? These are the things you guys have called it. And in the future with quantum, we'll also be protecting that, because with a quantum computer, you'll be able to attack a system like this if it doesn't have post-quantum, and then be able to tell the network everything's fine, basically, because you'll be able to manipulate of the encryption. So let's just key in the audience a little bit on these proof of concepts. So in Ethereum, there's proof of stake, proof of work, those kinds of principles, and then now we have these proof of security things. So did you want to talk just like a little bit about how they're similar, how they're very different, just to give everyone an idea of how it works?
Sure. I mean, in many ways, they're similar. In other ways, they extend what exists to fundamentally new areas. So they really, the biggest difference, I would say, for example, compared to proof of stake, is that, of course, this is like a Byzantine fault tolerance system that is custom, and it does all these things. But it does all these things not over, a smart contract that has been called by, a system with a key. It does all these things using smart contracts, maybe, but it does that over the systems themselves. So the systems themselves, the data, the applications, the processes, the services, the operations, any sort of like digital proof that you want to create of any digital process that's, really running digitally on a server somewhere, is actually provable and transparent, if you want, anywhere in the world for anybody. Right? And if you think about it, you're really creating the capability for machines to trust each other, right? And for you to trust the process that you have no access to, right? It's in a server that maybe you don't even, you might be consuming an API that belongs to someone else. But how do you know that the system that created the data, that sent the data to another system that consumed it and transformed it, and then sent it to the system that has the API? How do you know that they're all trusted? You have no idea, right? Nobody has any idea. Nothing is measured. So in the end, the objective was to create a hyper-measured environment that is incentivized. So the participants, the nodes, the validators are actually incentivized to provide this service, this value to the world. That, if you think about it, it's quite powerful. It really changes the way how you deal with risk in probably other things as well.
Well, that's a good point. I mean, I used to run big data centers, and the metric that I managed to was network uptime, 99.9, 99.9999, because it's all we had. And we could measure that. We could hire people. We could fine people if they didn't produce. But I think we're now in a world where the measurement is actually based on security, and we have no idea how to measure that. So when you talk to people who aren't technical, they say, yes, I want security. Like, yes, I want privacy. It's binary. Either you have it or you don't. But it isn't. It's, as we all here know, it's a continuum. And this allows us to really smoothly manage that continuum of what trust and security means. And there's an ancillary benefit from this, and this is getting a little futuristic, but we're about to move into the era of, I would say, semi-sentient software, or at least highly autonomous software. And the kind of thing, the way Naoris Protocol is working, fits that model a lot better. It's not a human being centric thing. It could, a semi-autonomous software entity could easily start talking that way and use relative trust in these
resolvers. And it sounds like there's some AI involved here, right? So with traditional smart contracts, code is the law, and whatever whatever conditionals they're going to follow, they're going to act on them in a Turing complete fashion, even if it means you clean out billions of dollars in funds, like during an attack, like the Dow or something like that. So that's sort of like brainless following of quote unquote logic. But when you add AI into the mix, you can do a whole lot more, I'd imagine. So what are these contracts doing? Let's just walk through a very simple example. It's kind of like a mesh, right, of these nodes. And let's say someone attacks one of them. What happens at that point?
It's so interesting you asked this question because, David was just talking about that. And you were also like, it is a mesh, and there are smart contracts. However, our consensus mechanism allow us to do more than what David was saying. So uptime. Let's talk about blockchain validators. Every blockchain validator that exists or miner is managed by one thing. Are you up? If the answer is yes, then validators be validating. That's what they do. But you have no idea if it's a trusted. If it's a trust, exactly like an SMS relay. Like of course, it's a lot more complicated than that. But the point is, you have no idea if you can trust them. Yeah, sure, it's decentralized. It's much better. But for example, one of the mandates that we had from former NATO leaders to use this, for example, in defense environments and to bring it, blockchain environments or decentralized systems to the real world was to make sure that all the participants are in a trusted state. It sounds obvious, but that is not something that exists, right? So we had actually to create the decentralized proof of security to ensure that, so that every participant that is in a green state or trusted state and maintaining their integrity and doing best practice, so on, and online can validate, right? And can participate. And if they are not, if somehow, as you say, one participant is hacked, something has been tampered with, or its uptime is not good, or a number of other parameters that, by the way, are completely custom, then can be as complex or as simple as you want, which gives you a lot of use cases, are broken, it doesn't participate. It cannot participate. You don't want a malicious actor. So it's a lot harder for you to have like a 51% attack and any other, kind of like traditional issues that you would have in blockchains. However, even if nothing of this was present, and I'm just going to defend blockchains in general, this is really already, without anything, but we're adding a lot more, already exponentially better than what we have right now, which is like, you hack one and, congratulations. After a while, you can exfiltrate data or ransomware the whole thing, right? Really, whatever you want, generally, if you're a capable attacker.
Can you give us like a real world example of maybe a customer, if you can't say the name, that's fine, but of how this was implemented and what particular way they chose? Because this could be flexible, right? You could be protecting IoT devices like we talked about earlier. You could be defending just about anything. So can you give like one example of how it was implemented?
Sure.
And then what happens basically at the end to just let everyone understand how AI comes in? Like, does it reach out to some centralized AI for decision or something like that? And then that should just kind of
I'll talk to you about that as well. So there's an AI system that we have that's called Swarm AI, and it's a consensus based AI ecosystem that basically gathers data and learns from edge computing. We wrote a paper as well with a couple of universities that actually got published and peer reviewed in a nice journal in Germany about IoT some months back about exactly this and how it uses the consensus mechanism for that and so on and so forth. So I won't go into details of clients, but I will tell you like, a real world situation with the proper obfuscation points. So you have an environment that have a collection of devices, like you have routers, you have, antennas, you have drones, you have, 5G things, various, 5G IoTs, you have servers in the cloud, you have virtual systems, you have Dockers, you have all these things locally in the cloud as well. And your infrastructure is distributed around the world. Sounds like a normal company. So a normal company is already decentralized. They just don't know it. So we're allowing for them to actually leverage that capability to defend themselves. And what happened in this case, this was actually, I cannot talk about real world attacks and mitigation for obvious reasons, but I can talk about, examples that we have actually, attacks that we have done on infrastructures. So I'm talking about an attack, for example, on a robotic arm that was in one of the company's networks that is part of the whole mesh that is the company. Mm-hmm. And this robotic arm, was running, an embedded Linux version. And the piece of malware that was put there, we made it FUD, or fully undetectable, by using a crypter for $0. That's how hard it is. That we got from the dark web randomly. We got various, but this one worked better. We tested it on VirusTotal, and it was, there's nothing here. Okay, let's try it. So there was a number of vulnerabilities on the box. So we did some remote code execution, dropped the malware. We executed it with a remote timer in kind of like cron, basically. So we basically just changed that. And it got executed. And the machine got tampered with, obviously. The robotic arm started going crazy in the real world and trying to destroy the things around it. And systems that were, for example, in other continents that were part of the same peer-to-peer mesh that actually knew how that system should look and should behave and so on and so forth, didn't accept that change. So they acted on it. We had a smart contract that isolated that environment and didn't allow the potential threat to propagate, and allowed, for example, for forensics to happen. But we went a little bit further on the second level, because we did this various times, and we created what we call backup nodes that are basically what they sound like. They are validated, trusted nodes that back up critical areas of data that you can define. Could be like specific folders or whatever. And if any of these things get tampered with, the system gets automatically reset and isolated under consensus and then turned on again. So what happens is that the robot was going crazy, and then after a while, it's checked again, it's rebooted, and it's checked again to be in a good state. Everything that was malicious was substituted or deleted. The malicious files that were modified, that were actually malicious movements for the robot, were substituted with the original ones, and everything was back to normal. And this happened in about like two minutes, but the initial detection and reaction was like 10 milliseconds locally on the network. So they detected it first, and then the global detection happened about 1 second later across all clouds. And what happened is that the swarm AI has learned about this potential threat and what it does, and it shared that across the rest of the ecosystem. So say, if there was another similar system in a different country that potentially was using the protocol, potentially on a different network and potentially on a different company, they could actually be protected against that, even though they have no idea that has happened somewhere else. And one of the biggest issues that we have, for example, and I'm just going to focus on cyber, even though we're getting into the world of decentralized infrastructure and, like this decentralized physical infrastructure, DeepIn and things like this. I have no doubt this is going to be the biggest area in blockchain in the next years. This is a DeepIn situation. So we have a decentralized physical infrastructure AI that's like on the whole environment or in a collection of environments, learning and improving. And all of that data is actually written to the chain and protected at post-quantum level. So even if your systems are not at post-quantum level, which they should be eventually into the future, with post-quantum keys, securing like SSH and SSL and all these things, even if they are not, the truth about them is. So you actually know what is instead of not knowing or guessing, because right now the time for detection of any threat is about 279 days, I think, in the US. The rest of the world is way more. So in our case, that was reduced to 10 milliseconds under this principle. So this is one of the use cases of the, let's say, the primitive we have created at Naoris Protocol. There's many more.
Is it safe to say that this might be able to catch 0 days just because there's an anomalous behavior on one node that was attacked, and then the other nodes could say, we don't know what this is. There's no, number associated with the vulnerability, but we know that we don't like this behavior, and we're not going to let that change happen to us. Is that kind of the idea?
That's a very good point, because changes, as you say, changes they assume integrity, right? Mm-hmm. And integrity can even be pushed at post-quantum level. So integrity is pretty close to mathematically perfect as we know it, right? It either is or it isn't. There's nothing in the middle, right? And under a decentralized validation structure, that gets very powerful. Obviously, blockchains are perfect at this. That's what they do already, mm-hmm. right? So we have extended that from bitcoins and smart contracts into data and systems and applications and services, right? Which is the rest of the digital infrastructure globally. So yes, your assertion is I would say is correct. Having said that, to be fair, there's probably thousands of different ways to skin a rabbit in terms of 0 days. There's exploits that have nothing to detect. There's so on and so forth. But eventually something has to happen somewhere. Otherwise, the attacker is doing nothing else but wasting their time.
Absolutely. So you're able to take this technology and make it post-quantum. So what kind of advice would you give to anyone else operating in this space for what you've learned and what you've accomplished? What should they be doing to try and make that migration too? If they're currently working on some kind of blockchain or some kind of technology in that space, what should they be doing in the short term now that we know that the threat's expanded?
I can maybe speak about all the environments that we have had contact to recently. I'm talking about Web3 spaces. So the problem is all the same. Banking, ports and rail, other critical infrastructure, nation state agencies, central banks, so on and so forth. They just need, to start with, they just need a plan. They just need, for example, to follow the strategic European data protection initiative on post-quantum, for example. There's one in the US as well that basically allows them or helps them create a framework that allows them to manage their own structures. So, prepare their libraries, prepare their systems, prepare their policies for transformation, right? Which in the end, it's not really painful. It's not like, yes, it's kind of like taking some hundreds of COVID shots for systems, but it's something that is much better than the alternative, which is, harvest now and decrypt later, and all your secrets being revealed, your 5-year plans, your IP, so on and so forth. And I'm sure David has something to say on that too. David.
Well, I would just add to that. I worked in big companies, and large enterprises move very slowly at adopting even incremental changes in their base software. I can only imagine how they're going to deal with this stuff, because this is not incremental. This is going to be significantly different than how they do things. So I would advise anybody that they should be starting pilot programs now and evaluating things like us and maybe our competitors, and start coming up with solutions and how they're going to integrate it into their enterprise.
And it's going to take years. Sorry, go ahead.
No, I was going to ask if there's a way for people to see like a demo of maybe the regular, the post-quantum version, whatever, just so they can understand how easy it is to implement something like this.
Yeah, so we have basically we have that available. For a number of reasons, we don't show that yet publicly because we are not public yet. But we should be in the end of quarter 4 if everything goes well. Also, assuming that the market gets better. And actually, these days, I mean both markets, the real world and the crypto one. Basically, companies, institutions, companies that would like to partner, etc., they can contact us, and we'll basically open up our doors and integrate with them and work to fix their problems either in a very custom way or help them build on our chain. or integrate their existing software or systems in our chain, which is actually quite easy. In most cases, it's kind of like just wrapping code around something.
Yeah. So with that call to action, I'll thank you guys for your time, and I'll definitely be linking everything about the Naoris Protocol in the show notes. Thank you.
Thanks so much, Konstantinos. It was a pleasure to be here.
Thank you.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today, in case things got too nerdy at times. Let's recap. Naoris Protocol is a blockchain designed to protect network devices. Typically, the larger a network becomes, the larger the threat surface grows, providing more potential points of failure. With Naoris, the more nodes that come online, the greater the protection, including handling some devices that have proved challenging to organizations in the past. Each node validates that a device or application is safe and maintains integrity. Suppose bad behavior is detected, such as a hack. In that case, the network will no longer trust the device through consensus among the many other nodes. This is similar to how a cryptocurrency blockchain would not accept forged transactions. One of the NIST PQC finalists, Dilithium, is now being used in a version of the Naoris protocol. The hope is to add this post-quantum cryptography to the main chain's proof of integrity or validation of all devices. Devices that run Naoris nodes can be servers or lighter ones such as phones or IoT appliances. However, nodes can also run on industrial systems, which can potentially cause physical harm if hacked. For example, the protocol can protect industrial robots. This could prevent at least one kind of robot uprising in the future. While Naoris is still new, the team has worked with high-profile environments. Blockchain is a natural fit for validating devices, and launching with post-quantum cryptography as an option is a terrific example of how PQC is starting to appear across the industry. Because so many blockchains are vulnerable to quantum computers, I'd like to see more PQC development in the distributed ledger technology space. That does it for this episode. Thanks to David Carvalho and David Holtzman for joining to discuss Naoris Protocol. And thank you for listening. If you enjoyed the show, please subscribe to Protiviti's The Post-Quantum World and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protiviti. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protiviti.com or follow Protiviti Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.